of MLIR toy language generation. Today we will focus on MLIRGen.h and MLIRGen.cpp. So I will remove all of these coding and then type again from start. What this code is doing is it's basically converting AST into toy dialect, which is a dialect in MLIR, and we defined the MLIR class, MLIR dialect class, and also defined the superclass of all toy operations. And we also have a defined operators like add up, func up, generic call up, something like this. And the program language looks like this, defining user function, and also having tensors like this, and calling user-defined functions like this. And we have element-wise multiplication for the tensor type. So this is parsed by using lexer and parser, and then it's converted into abstract syntax tree. In the abstract syntax tree, we have a different kind of tree nodes like return, num, literal, variable, binary operator, call, print. So each of these abstract syntax tree nodes will be converted to dialect, toy dialect. So what we're going to do today is converting AST into MLIR dialect. Okay, so remove all. Another namespace called toy. In the toy namespace, we have a class module AST, and I'm not going to type all these comments, but copy it, and my friend will speak instead of me.
I offer the given toy module AST returns a newly created MLIR module or nullter on failure.
First have a context for the first parameter, and then the second parameter we have a module AST. Module AST is from module AST will be defined, and I think this should be the abstract syntax tree, and this is the result of toy dialect. But we will see what's going to happen. Next one is MLIRGen.cpp. Remove all of them, and then I first start to type in function signatures and then type all the bodies of the function signatures so that we can see the inside of we can see the brief module structure and then implement functions. Builders. We have lots of input files because this is the main file. Okay, we are done with the boring part. Now we will continue, but because I don't copy all these comments, I'm gonna just copy all of them.
Implementation of a simple MLIR emission from the toy AST. This will emit operations that are specific to the toy language, preserving the semantics of the language and, hopefully, allow to perform accurate analysis and transformation based on these high-level semantics. Public API, convert the AST for a toy module, source file, to an MLIR.
맞출 오퍼레이션.
Module, AST. Okay, we'll keep going. Private
module matches the toy source file, containing a list of functions.
So this is basically a file. Builder. Next we have a builder.
The builder is a helper class to create IR inside a function. The builder is stateful. In particular, it keeps an insertion point. This is where the next operations will be introduced.
Oh, I typed the next one. Builder. Third one is a symbol table.
The symbol table maps a variable name to a value in the current scope. Entering a function creates a new scope, and the function arguments are added to the mapping. When the processing of a function is terminated, the scope is destroyed and the mappings created in this scope are dropped.
It's like something like a call stack maybe. Okay, I think it acts like a stack. Whenever a function is called, entering a function means calling a function, creates a new scope. New scope means variables or parameter values mapped to function arguments. And then it's destroyed after the scope is dropped.
Helper conversion for a toy AST location to an MLIR location.
This is location. The next one is
declare a variable in the current scope. Return success if the variable wasn't declared yet. Create the prototype for an MLIR function with as many arguments as the provided toy AST prototype.
creates the prototype for an MLIR function with as many as arguments as the provided toy AST prototype. So prototype AST is function name, location, and the vector of arguments. And each argument has a variable expl AST. Variable expl AST. So expression. Function name, expression name. Okay, so this is simply holding a name and location, and also names of arguments. Emit a new function.
Emit a new function and add it to the MLIR module.
emit binary operation.
This is a reference to a variable in an expression. The variable is expected to have been declared and so should have a value in the symbol table, otherwise emit an error and return null. Right curly bracket. Emit a literal, constant array. It will be emitted as a flattened array of data in an attribute attached to a toy constant operation. See documentation on attributes, MLIRGen.h attributes, for more details. Here is an excerpt. Attributes are the mechanism for specifying constant data in MLIRGen. Places where a variable is never allowed. They consist of a name and a concrete attribute value. The set of expected attributes, their structure, and their interpretation are all contextually dependent on what they are attached to. Example, the source level statement.
파의 미면 2, 3, equal 1, 2, 3, 4, 5, 6.
Will be converted to
%0 equal to 2 transcription 계류, 댄스, 텐서 미면 2 곱하기 3xf 60.
Collect the data.
Recursive helper function to accumulate the data that compose an array. Literal. It flattens the nested structure in the supplied vector. For example, with this array, comma, 1, 2, 3, 4, we will generate, comma, 1, 2, 3, 4. Individual numbers are represented as doubles. Attributes are the way MLIR attaches constant to operations.
Individual numbers are represented as doubles. Collect the data.
Emit a call expression. It emits specific operations for the transpose. Built-in. Other identifiers are assumed to be user-defined functions.
Specific operation for transpose built-in. Other identifiers are consumed to be user-defined functions.
Emit a print expression. It emits specific operations for two built-ins.
트랜스포즈 x and 프린트 x.
Emit a constant for a single number. FIXME, semantic, broadcast. Dispatch cogent for the right expression subclass using RTTI. Handle a variable declaration. will code the expression that forms the initializer and record the value in the symbol table before returning it. Future expressions will be able to reference this variable through symbol.
테이블 룩업.
Recording expression deforms. So variable declaration is name, type, initial value. Looks like it's for constants.
Code in a list of expression, return failure if one of them hit an error.
List of expressions, return failure if one of them hit an error.
Build a tensor type from a list of shape dimensions. Build an MLIR type from a toy AST variable type, forward to the generic.
Ch2 above.
Var type is simply a variable type with the shape information. It has a shape which is a vector of int 64, and it's just calling another function which accepts a list of int 64 shape. Okay, we're done with all of these prototypes. Let's start from the top level and continue to go through each of the functions by clicking on the function name instead of implementing each of the functions from start to end, because I prefer to write in code like this because it helps me to understand the code much more easier. So we are having module AST. Module AST is put into MLIRGen impl, the class we are going to implement above, and then we are calling MLIRGen in the class, but we're passing the context as the first argument of the constructor. Let's go to here. Module AST, we have to go to module AST. Yes, this one. Let's just start typing from here. This is something we're gonna type.
We create an empty MLIR module and coagent functions one at a time and add them to the module.
So now we can understand the code a little bit in this file, which is the module, and each module has user-defined functions like this. This is the main function. We have two functions, and each of these functions are going to be into this loop. So module AST, let's go to module AST, and what is there? It has a list of functions, and each of the function is having type function AST. So for each function AST, we are, but I'm not sure how this for is working. So let's just see module AST. It is vector, begin and okay. It's implementing two methods, begin and end. It looks like this is making the module AST as an iterator for the for in C++. So second part is here.
Verify the module after we have finished constructing it. This will check the structural properties of the IR and invoke any specific verifiers we have on the toy operations.
It's pretty straightforward because one module has multiple function ASTs. Module ASTs having multiple function ASTs, so we are going to call MLIRGen for each of the functions in the module. So MLIRGen with the function is here. So I'm going to type in this one first because this is a top level function. The code we're going to type is pretty long, but it won't take a long time. This one is the code we're going to type in. Let's first try to analyze. Okay, I decided not to analyze right now, but just start to typing.
Create a scope in the symbol table to hold variable declarations.
Looks like this is a symbol table for arguments and local variables. So the reason we are passing symbol table here is because it looks like this symbol table has the same type with the one we are going to create, and this is going to be a parent symbol table so that we can access to the global variables. But let's make sure it is a parent type. Scope to hash table scope. Create an MLIR function for the given prototype. So it looks like we are setting the MLIR code insertion point at the end of this module. Get proto. I think this star is working like this, but for the brevity I'm gonna remove this parenthesis. If not function, return PTR. So func up looks like is a smart pointer. Func up, let's see, what is a func up? I think it's here. No. Yes, we have a func up here. It's generated by processing ops.td. Why we can return null PTL for the func up? I'm investigating the issue here. So func up is basically MLIR op. I'm not sure right now. I skip it. Let's just start the body of the function now.
Let's start the body of the function now.
Each function has a block, at least one block. Function.
declare all the function arguments in the symbol table.
Okay, so we're gonna iterate the function arguments and then put into the symbol table. Put them into symbol table const r name value. Zip 4. The first one is a proto-args, so each of the arguments here get args. It's returning expl ast, and each expl ast is having expl is ast, the root is the superclass of all expressions. So get name should be from expl ast. Oh, we don't have get name. Enter block dot get arguments. Enter block. list type. So the second one is a block argument, entry block argument, and the prototype arguments. These are zipped and what's the LFVM zip? I'm logging into Ch2. Okay, I see. So AB is going to x and y, and x plus y is going to be 5, 7, 9. 5, 7, 9. Okay. So this is from
Set the insertion point in the builder to the beginning of the function body. It will be used throughout the code to create operations in this
function.
The entry block is from the function that front, and the function is from MLIRGen. So MLIRGen is creating function from the function prototype, and then after this is created, it has the first block, and we are moving the insertion point into the beginning of the function, which is the entry block.
Emitter body of the function.
So it's basically generating prototype first and then generating body. Func AST has a body as well. Let's see what it is. AST has body. So body is type of EXPL AST list. Okay. It's basically list of EXPL AST, which is the superclass of all the expressions.
Implicitly return void if no return statement was emitted. FIXME, we may fix the parser instead to always return the last expression. This would possibly help the REPL case later.
So the last operation of the entry block should be return.
Otherwise, if this return operation has an operand, then add a result to the function.
function that set type, get function type, builder that get function type, builder. Function is a function operator, and builder of builder. Let's see what the type of the builder is. Op builder, okay. Op builder. MLIR op builder. Let's just see get function type first. Range. Type range classes. Various different ranges of value types.
This class provides an abstraction over the various different ranges of value types. In many cases, this prevents the need to explicitly materialize a small vector stroke std vector. This class should be used in places that are not suitable for a more derived type, for example array ref or a template range parameter.
Next, we move on to function that get function type that add inputs. Function is this one, func op, get function type. In func op, we have a get function type. Okay, we have it here. Get function type. Get inputs. So MLIR get function type has function type. I'm lost here. Okay, I'm gonna skip because we have to type in another function. What's get type here? Get type, okay, get type. What's part type? Oh, okay. So it's having no shape at all because it's empty. Because it has no operands, it's just creating an operand without any, without type, without any shape. Okay, now we can move on to two functions. The first one is MLIRGen receiving get proto. Get proto is prototype ASD, and prototype ASD is location, name, and arguments. Let's go to this one first. Proto ASD. Yeah, this one. This one is for creating the function prototype. It creates a func operation. So the abstract syntax tree has a lock LOC, and this is used when we create a MLIR. When we generate MLIR, we are referencing this location of this function prototype AST.
This is a generic function. The return type will be inferred later. Arguments type are uniformly unranked tensors.
I'm not sure why we are passing the type as void type here. I think this is void type without any shape. So the after the MLIRGen returns a func output, it doesn't have any shape information for each parameter. Next function we have to type in is MLIRGen getBody. GetBody is expl ast list. This is another long function. I have to type all these in.
Specific handling for variable declarations, return statement, and print. These can only appear in block list and not in nested.
익스프레션즈
MLIRGen with the expression AS list is checking each of the expression in the block and then see if there is a variable declaration or return or print. If each of them is found, then we have a special handlings in these function if blocks, and then process the expression for MLIR generation, and then if anything failed, then it's returning MLIR failure. Otherwise, we are returning MLIR success. Because we have various versions of MLIRGen with the different types passed as the parameter, we first have to do dynamic cast for the expression and then check the type first and then pass it to MLIRGen so that the correct function is called. Print. Now we have 4 functions we have to type in. The first one is a variable declaration, and then return, and then print, and then other expressions. Let's just start from the variable declaration. This one. First, we get the initial value from the abstract text tree, and then try to generate value from the initial value.
We have the initializer value, but in case the variable was declared with specific shape, we emit a reshape operation. It will get optimized out later as needed.
If the shape is not empty, I'm not sure how this is created. Reshape up. Let's try to see here. It is one argument. Looks like a get type is returning the result. Oh no. This one. Get type returns this one. Not sure how this is created reshape over here. Let's just see the generated files. Type and value. Now finally we register the value in the symbol table. see what is this one. Okay, either a block or operation can own this value, and in the value we have a value in pool, and this is just simple wrapper of the value in pool.
This class represents an instance of an SSA value in the MLIR system, representing a computable value that has a type and a set of users. An SSA value is either a block argument or the result of an operation. Note, this class has value type semantics, and is just a simple wrapper around a value in that is either owner by a block, in the case of a block argument, or an operation, in the case of an op result.
How about we finish this function by implementing MLIRGen with the EXPL-AST. Yes, this one maybe. Oh, here. So it's basically dispatching code gen. Default is error. because we have a different kind of expressions here, I'm not going to type each of them right now, but go to variable declaration again, and let's just say that we have finished this part, and then I think we're all done for this one. So this is done. So let's clean up the second one. Return expr. Return expr has optional expression. Return explast. We don't have a return. It's very interesting. We don't have any return expression processing. So it's gonna come here, and then because it's a return, I'm lost. Okay, for now I'll skip it. Next one is a print explast. Get arg is returning explast in the print statement, we have only one argument. It's pretty straightforward. First, to generate MLIR code for the argument of the print, and then create a print op using the argument. So I suspect that this build function is generated from print op, and the print op is here. And arguments, it has only one argument. But the part I didn't understand was reshape up. Reshape up has arguments, input argument and return argument. It has two. So reshape. I don't really understand this one right now. I think this is return type. Particle that get type. Particle that get type. I'm guessing this is the return type. Okay, it's generated by Ch2. Looks good. Code, oh, sorry, code color, not Ch2. We are finished yet with the return explast, so let's go to print explast. Oh, it's done, okay. So what's left is a literal explast, call explast, and print explast is done, and number explast. And also get shape. How about finishing these simple functions first? The get shape. So we get type.
If the shape is empty, then this type is unranked.
Otherwise, use the given type. number expLAST. So get value returns just a double value. So constant op is going to, let's just see, constant op. Results arguments. Coal. What's operands here? Suddenly, oh yeah, operands easy. This one. Okay, small. It's just a vector of a small vector having just a few elements, and if the element is less than the predefined number in the inline the array, then it is not going to allocate from any heap memory.
It contains some number of elements in place, which allows it to avoid heap allocation when the actual number of elements is below that threshold. This allows normal small cases to be fast without losing generality for large inputs.
노트.
In the absence of a well-motivated choice for the number of inlined elements n, it is recommended to use small vector t, that is, omitting the n. This will choose a default number of inlined elements reasonable for allocation on the stack, for example, trying 2.
킵시지 앞 스멜 벡터 t 어라운드 64 바이프스.
Call is transpose, we're going to do something special. We're going to check if the number of characters is just 1, and then create a transpose op. So this is internal function. Okay, we have a collect data, but before implementing collect data, we will implement MLIRGen with a little XPL AST first, because it looks like this one is used by this one. I'm not sure where this is called. Oh, here. EXPL literal and in the vertical the init value is expl.ast. Get init val looks like get init val is going to have a literal. So this is called, probably this is called from the variable declaration for the initial value, like this. Get themes is looks like a values and dimensions. It has values and dimensions. So we are calling the get type version of this one int64 array ref. We have an int64 array ref, so the shape dimensions are put into this function, and because the shape is not empty, we are creating ranked tensor type.
The attribute is a vector with a floating point value per element number in the array. See collect data below for more details. Looks like dimensions are multiplied and trying to get the number of elements in this vector. Starting from 1, looks like this is an initial value. Multiplies is a binary function object class that implements an operator to return the product of the two arguments.
and then we collect the data. So collect data is simply flattening the constant values, flattening the constant tensor into an array, and it looks like we are going to reshape it after collecting the data.
The type of this attribute is tensor of 64-bit floating point with the shape of the literal.
So this data type is a ranked tensor type with the shape here. Looks like the first parameter of the ranked tensor type is a shape arrays. Shape array, and then element type is the type of this ranked tensor.
This is the actual attribute that holds the list of values for this.
텐서 리터를
Build the MLIR optoy constant. This invokes the constant build method.
Very interesting. Data attribute. Dense elements ATTL, which is a type, and this type has this dimension, this shape, and then data, collected data is passed. What's the data? Is double vector. So array ref with the double vector is passed. Okay, now we collect the data. It's recursively calling collect data. Get value of a literal explASTs. Get values. So literal explAST is going to have a list of explAST values. The parser is simply flattening these values like this. Okay, we are pretty much done, except these two functions, I think. Oh, we have more. Let's just go to the start and finish this one. Finish from this one. Location. Oh, it's pretty simple. Just one line. Line. But why we are using this function get string attr from this one look.file location is like this. Now let's move on to the declare function. We are declaring variable in current scope return success if the variable wasn't declared yet. Who is calling this? From function AST for the entry block arguments, we are running declare. a function or in a function. Assert. Why this is red? Oh. The last one.
First, emit the operations for each side of the operation before emitting the operation itself. For example, if the expression is a plus foo, 1, first it will visiting the LHS, which will return a reference to the value holding a. This value should have been emitted at declaration time and registered in the symbol table, so nothing would be cushioned. If the value is not in the symbol table, an error has been emitted and nullter is returned. Stroke 2, then the RHS is visited recursively, and the call to foo is emitted, and the result value is returned. If an error occurs, we get a nullter and propagate. Stroke.
Basically, this is generating 2 arguments. Are generated first. Then we have a special.
Derive the operation name from the binary operator. At the moment, we only support +an.
What's ghetto P? Ghetto is just within a character. Where is the location? These 2 are all operations supported. All the operations are, all the binary operators are invalid, so we have to enter an error. I think we are done now, but before going forward, let's see who is setting the location. Call expllast. Prototype AST. Okay, so Looks like the location is set in another function. But why not using this binary expression AST location? I don't know. Let's double check if you are done with all of the functions. I'm pretty sure we are done. Okay. Good. Let's try to compile. Oh, so many errors. Function body after MLIRGen.h is 19. Sorry. Oh, still 20. Module of MLIRGen 41. Baskin Robbins 41. This one module of unknown type module AST 41 module AST. Toy. Something's wrong here. Oh, namespace toy. Still 20. Oh, still 20. So many errors. Oh, I see. This one is missing. Oh, now we're 7. Now we have only 7. Symbol table. Dot lookup. Where is the symbol table? Oh, here. Symbol table. Two. variable var. Yeah, this is something I'm gonna say. We don't really have a function that is. I'm gonna find this one. Let's check. Oh, I guess I was missing this one. Right after variable expLAST. I missed this one.
Return takes an optional expression. Handle that case here.
Optional expression, so has value. If the return expression has value, get expr. Oh, very good. Copilot is really helpful, and the latency is so low. I'm pretty much satisfied with the Copilot. Four more errors. 49. Oh, looks like I'm missing the const. No? .h const. Why const here? No const. I was wrong. Okay, we're done. Thank you for watching. We are done with the chapter 2. Tomorrow I'm going to start again with the chapter 3. To wrap it up, we have at the first session we typed in ops.td, which is defining toy dialect, and then each operators in the toy dialect. These are auto-generating DSLs of MLIR. The auto-generated files are here. These are included into this project. And we have abstract syntax tree, lexer, parser. All these are converting the source program, which looks like this one, into abstract syntax tree. And abstract syntax tree is converted into MLIR using MLIRGen function, and this one is the one we typed now. And dialect.cpp is providing necessary functions for each operation. Okay, thank you very much.